Okay, we have this problem here. Colors A and B are connected by a 25-inch long wire. So AB equals 25 inches. The colors can slide freely on a frictionless rods. All right, frictionless rods means that there will be a reaction on the colors perpendicular to the rod, perpendicular to z-axis on color B and x-axis on color A. Determine the distances x and z. So the question is x and z, for which the equilibrium of the system is maintained when P equals 120 pounds, and Q 60 pounds. 60 pounds. All right. Okay, so if we need x and z, well, x and z are part of the vector AB or BA, right? Because in order to go from A to B, we need to move this x amount here in the x direction, x, we go down 20 inches here and then c inches in this direction. So that's a good clue about how to find the solution for this problem. So let's set up the vector AB. AB will be equals to, in order to, from A to B, we need to move x in the direction I negative. We have to go backwards in the sense of the x-axis minus x. We need to go down in the y direction 20 inches, so minus 20 inches j, and z in the direction of the axis z, so plus z k. So, and we know that the length of the wire is 25 inches long. So we know now that the 25 square is equals to x square plus 20 square plus z square. So we know here that x square plus z square equals to 25 square plus minus 20 squared, so this is 225. Okay, so we have this first equation that, well, it's going to be useful. So now we need to get just another equation, and we have two equations with two unknowns. Well, the other equations that we can set up in here are the equations of equilibrium of the colors. So we have to use those equations because the distance x and z are the necessary distances to maintain the equilibrium of the rod. So let's set up equilibrium equations. In order to do that, what we have to do is to set up first, set up a free body diagram of the colors. Let's start for the color at A. Let's do the free body diagram of A. Let's do some system of axes here for color A. Let's put a y-axis here, an x-axis here, an x-axis here, and a z-axis here. Then let's put the color here, color at A here. This is going to be the particle that we are going to study. This is the color A, the color at A, that slides on the rod that is oriented in the x direction. So let's draw the forces that are acting on color A. First of all, the force P is acting on this color, force P. P equals 120 pounds. There is another force produced by the rod AB, the cable AB. Let's put it down here like this. And we're going to label it tension AB. Tension AB. And there is also the reaction of the rod against the color A, which we know that the rod is frictionless, so there is no component on the x-axis. So that force has to go into the YZ plane because that force is perpendicular to x. So let's put it here. Let's call it N, is a normal force perpendicular to the rod. We don't know that force, we don't know what is it, in what direction goes, but we just assume any direction that we want, and then if we need to find it, we could find it. Let's decompose this force into the rectangular components. So we will have here vertical component that we can call NY, and horizontal component that we can call NZ. What other forces we have here? I guess that's it. So that will be the free body diagram of color A. So let's see if we can write down all the equations, all the forces in a rectangular component, so we can write the equations. First, we have the P force. The P force in rectangular components is just a force in the x direction, so just 20 pounds I. Then the normal force, I already talked about it, so it has two components. There is no component in the I direction, so only N, Y, J in the positive direction, and N, Z in the negative direction, the way I assume. So NCK. NCK. Now the force on the cable AB. The force on the cable AB, we are going to decomposing the rectangular components based on the magnitude and the direction. So we are going to express it as the magnitude of the force TAB multiplied by lambda AB, which is the unit vector in the direction of the bar of the wire AB. So that will be the magnitude AB multiplied by the unit vector, which is the vector AB divided by the magnitude of the vector AB, which is 25 inches. So the tension AB will look then like magnitude multiplied by lambda AB, which is 1/25 inches, multiplied by the vector AB, which is minus xi, this guy right here, minus 20 inches, J plus CK. All right. So we have all the forces in rectangular components. So now we can proceed to set the equilibrium equations. Summation of forces in the x direction equals to 0. So we have to add all the forces with I components, like this one and this one. So that will be 120 pounds. Oh, let me put that in blue. I'm writing in blue here. £120, and then minus this component here, minus TAB over 25x, TAB over 25 inches, x, and there is no more components in the x direction, so that should be equal to 0. From here, we can get this equation, x TAB equals to 25 times 1, 20, which is 30,000 pounds inches. Okay, that looks like a good equation because it has x in there. Let's see summation of forces in the x, y, in the y direction. So in the y direction, we have, let me get rid of this and this. In the y direction, we have NJ here and this other component right here. So we have NY minus negative minus TAB over 25 inches times 20 inches. This equation is also, the summation is also equals to 0. So from here we get NY equals to 0.8 TAB. Okay, and the last equation will be the equation of summation of forces in the z direction equals to 0. So now we have to make the summation of all the forces that has components on the k or z direction. That will be this one, and will be also this one. So we have minus NC plus TAB over 25 inches Z, and that summation has to be equal to 0. So from here we get 25 inches NZ equals to Z TAB. All right. So we have another good equation right there. It's Z. Okay. Oh wait, but this one has another one. Okay, well, we have to set up the equations of the other color to see we can. So I can see that we can do anything here. We have too many unknowns. Let's set up the free body diagram of color B. If I can move this a little bit this way. something like this. So let's set up the free body diagram of B. Okay, let's put the color here. The forces on the color. We have Q, 60 pounds. We have the force on the rod AB, something like this. Let's call it the AB. And the force on the reaction on the rod is going in the C direction. This is the C axis here. So there is no component in the C direction, but there is components in X and Y because the force is normal to the Z axis. So let's draw the force like over here, in any direction over here. We can draw the components. They have to be normal to the Z axis. So this could be drawn something like this. Let's call this one N prime, and let's call this one N prime Y, and let's call this one N prime Y. Oh, Z. X. This is X. X. All right. So I have three forces. Let's express those forces in rectangular components. First, Q. Q has only component in the C direction, positive, so it's 60 pounds K. N prime. It has a component in the X direction, negative, and X I, and a component in the Y direction, negative, N prime Y, Y. And then we have the tension. There will be now, which we call it tension dA, which is equal, we can express this as the tension in the cable is the same AB, the same magnitude, not the same direction, but the same magnitude, so we can call it DAB. And the direction will be given by lambda from B to A, which is the same lambda from A to B, but with opposite sign. So we can write this as DAB multiplied by BA over the magnitude of DA is the same magnitude as AB, and we can put it here 25 inches. Is the length of the cable from A to B. So this tension DA can be expressed as DAB over 20 inches multiplied by the vector BA, which is the same vector AB but with opposite direction. So we can just change the signs of the vector that we have before here. This vector here, this is AB. So BA is the same but with opposite signs. We can put XI plus 20 inches J minus ZK. So you can verify that. You can verify that if you go from B to A, you will go from B to A. Let me see if I can increase the size here. It's not helping now. It's tired. It will be from B to A. In the X direction, you go positive in the X, positive in the y, too much, positive in the x direction, positive in the y direction, and negative in the z direction. So positive, positive, negative. So we have here positive, positive, negative. Okay, let's continue. So let's set up the equations of equilibrium. Summation, now let the summation for free body diagram of B. We have summation of forces in the x direction equal to 0. We have to make summation of everything with the I. So we do this one and this one. Minus n prime minus n prime x plus TAB over 20 inches. Actually, no, it's not 20, it's not 20, it's 25, right? It's 25 here. It's 25. TAB over 25, x equals to 0. So here we can write x TAB equals to n prime x times 25 inches. Summation of forces in the y direction equal to 0. So now we have to add, everything in the y direction. So that will be this one and this one. So it will be minus n minus n y prime plus TA over 25 times 20. This is inches, this is inches, equals to 0. So from here we get ny prime equals to 0.8 TA, where TAB is actually TAB. And that equation is same as the other one. It doesn't look like it's gonna help because it doesn't have x or z. Now summation of forces in the z direction equals to 0. We are going to add everything in the k direction, so that will be this one and this one. So it's 60 pounds minus TAB over 25 inches, z equals to 0. So from here we get 60 times 25, 60 times 25, 1500 pounds inches equals to CPAB. Okay. All right, so what we have here, a bunch of equations that are too big. This got too out of hand size. Okay, let's do this. Okay. Let's see what else we have here. So this is another equation. This is a good equation because it has C on it, and this one is going to has X on it, and if we divide it, we can get rid of the A, and we get something on X and C. So these two equations, we go X, A, X, A, T, A, B over Z. What is X, A? Just X. X, T, A, B equals 3000, and C and CTAB equals 1500. CTAB equals 3000 pounds inches equals 1500 pounds inches. So here we can obtain here that X equals to 2Z. That's interesting. And we used to have this. I am increasing the size all the time. Let me reduce the size a little bit so that it's a little nicer. Okay. So this comes from this and this. So we have now this relationship here, and we combine with this other relationship here. So X is equals to 2C. So 2C square plus C square equals to 225. So 4C square plus C square equals 225. So 5C square equals 225. So C equals the square root of 225 over 5 equals to the square root of 225 over 5, 6.708. And we know that from here that X equals to 2C, so equals to 2 times 6.708. So X equals to times 2, 13.416. So we got our solution, pretty nice here. X equals 13.4, C equals 6.71. All right, and everybody happy. Okay, that's it. Now you need to practice on your own. Look at the examples on the book. Look for other examples in the books. And YouTube has many examples also developed for you guys to prepare for your evaluation coming. Okay, thank you very much. Bye-bye.